Happy day, everybody. We made it. We're finally in Unit 4. Take a preview. It's entitled Application of Derivatives. Yay, we get to use derivatives all the time. But there is one last technique of taking derivatives that you have to learn. It's for a function that can come up when you least expect it, and it's called implicit. An implicit function, well, let's put it this way. You're used to having an equation solve for y. That's called explicit. That is because y is on the outside. You can solve this equation for y. So doing the derivative is very easy. You just say the derivative of y, we always say is y prime. But that really means dy dx is 6x minus 2. But what if you run across a function that is not so forgiving? 3x squared plus 5y minus 6x plus 2 equals 2x. At the moment, this function is considered implicit because y is inside the function. It's not solved for y. Now I know what you're saying. You could take 30 seconds of your life and you could solve this for y and then find y prime. That is true. But what if your function was 3x squared plus 5y squared minus 6y plus 2 equals x? Good luck. This function can be solved for x, but it cannot be solved for y. So you would not be able to differentiate that by just solving it for y and find y prime. Remember, the goal is to always find y prime. So let's get to it. Here's a whole bunch of reading. I'll give you a second to read. Just kidding. You know you're not going to read that. But let's look what's inside it. Implicit differentiation talks about a function solve for y, and I could do this problem y equals to the square root of 25 minus x squared. I can do my y prime, which I'll call dy dx for right now, using the chain rule. 1/2. Keep the insides. Negative 1/2. Now do the derivative of the inside times negative 2x. We rewrite that as 1 over. That negative 1/2 becomes positive 1/2 downstairs. 25 minus x squared. And there should be still an x on top. So 1 times x just gives me x. And there's a negative. Boom. Because the 2's canceled. But the negative x stayed there. And FYI, in case you didn't know, this was, and you should know from pre-cal, it was an equation of a circle. How do I know? Because what if I square both sides to cancel out the square root? Square both sides. Y squared is 25 minus x squared. Put the x squared on the other side. X squared plus y squared is equal to 5 squared, which is the equation of a circle centered at 0, 0 with the radius of 5. And why do I know it's at 0, 0? That's x minus 0 squared plus y minus 0 squared equals to 25. The center of the circle is right 0, up 0. So it's just that circle, up 5, 5, 5, 5. There's my circle. And I just did the derivative right here. This is, I did it explicitly, because y was on the outside. He's moving down. Talk about a different kind of function. This one is, he's telling me it is a circle. Okay, well, I'll have to take his word for it because it looks just like a bunch of variables. No, it's a circle. There's a reason I know from conic sections that was a circle, because x squared and y squared are in the problem, and the number in front of each are 1. So those numbers are the same. That tells me it had to be a circle. Regardless, the center is not 0, 0. Because you have x's and y's in the equation. So that's a circle. And if you remember, calculus can even be applied to implicit defined functions. This is implicit. You cannot solve this for y. We're going to solve this by hand. In this lesson, we will differentiate these functions that are implicitly defined. But it doesn't look like he's having us do it right now. I should teach you how to do it right now. Let me finish reading what we have here. It says that we will utilize an alternate notation for this derivative. Instead of f prime, we're going to use dy dx. We've talked about that before. It just means the derivative with respect, the derivative of y with respect to x. That's how we say that. It looks like he wants me to do this one implicitly first. The one that I just solved, already solved it for. We already had it written as solve for y. So I'll show that one first. If x squared plus y squared is 25, and I do the derivative of both sides without solving this for y. Now, mind you, we could solve this for y, and we already did do the derivative, but I'm going to do the derivative with respect, oh, I didn't want to do that. With respect to x, both sides. The derivative of both sides with respect to x. Distribute. Now, normally we won't do all those steps, but I'm just showing you all the details. Distribute the derivative all the way through. That gives me the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of a constant, 25. when you do the derivative with respect to x of x squared, it looks like this. Just a plain 2x. But internally, it was the derivative of x with respect to x. I end my answer with the derivative of x with respect to x. That lets the reader know what variable was I differentiating. Plus, the derivative of y squared with respect to x would be 2y. However, the variable is y. I have to say dy dx equals to, the derivative of a constant is always 0. So, was that a lot of detail? That might be after you've done 10 problems. You might not show every little thing, but we'll get the hang of it. Now, dx looks like any other fraction that you've seen. It looks like the derivative of x with respect to x is just a 1. So this piece turns into just a 1. Goes away. 2x. However, 2y dy dx does not go away, equals to 0. But the whole point was to find dy dx, find the derivative with respect to y. So I subtract the 2x, I have 2y dy dx equals to negative 2x. Divide both sides by 2y, dy dx is negative 2x over 2y, which is negative x over y. There's your first implicit differentiable function that we just did. Okay, the next page. Consider this picture, this graph. It's another circle. Find the equation of the circle. Well, we just did the equation of a circle that looked like this. X squared plus y squared was 25. That meant it was centered at 0, 0 because there's nothing being added to the x squared, and there's nothing being added to the y squared, equals to 5 squared. 5's the radius. That means I do not go left or right, and I do not go up or down. This particular circle shifted. And looks like, if I look close enough, trying to find where the exact center of the circle could be. Looks like it could be this diameter right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be the center. And the radius looks like it's 5 all the way. All right, so we found the equation of that circle. That would be considered as x. I went to the right 5. That's minus 5 squared. I went down 5. That would be y plus 5. It's always the opposite. Squared equals to the 5 squared radius, which is 25. We always do the opposite of what we see in the parentheses. Minus 5 means the x went to the right. Plus 5 means y went down. And that's what happened. This is talking about if you were moving from 0, 0. Whereas this problem was 0, 0. So that went to the 5 to the right, 5 down to get to the center. Did I go down 5? I think I messed up. I didn't go down 5, did I? I only went down 2. Wait a minute, I'm really all messed up. I should have counted better. It only went 1, 2, 3 to the right, down 2. Wow. I was thinking of that radius the whole time. It was 3, 2. X minus 3, y plus 2. Wow, was I off? I wasn't even thinking. Anyway, there's my new circle. I would have known it if I had wrote the order pair. It was 3, negative 2. That's the center of the circle. All right, now implicitly differentiate this thing. I could implicitly differentiate just the way it is. And I should do it both ways. I could differentiate this from left to right by doing the derivative with respect to x of the left, and then the other side would be derivative with respect to x of that constant. Guess I'll do it. He didn't tell me to expand it. When I take a derivative of x minus 2 all squared with respect to x, the 2 goes on the outside, x minus 2 on the inside, take 1 away from the power, go in and do the derivative of the inside. The derivative of the inside is nothing more than the derivative of x, which is dy dx. I'm sorry, it's not dy dx. It's not a y. It's a dx minus 0. Then I go to the next part, plus the 2 goes in the front, keep the inside, y plus, y, what was it, y plus 3, 2y, 2 times y plus 3, take 1 away from the power, go on the inside, take the derivative from left to right. Derivative of y is dy dx plus 0, all equal to the derivative of 25 is 0. So it doesn't look too bad. I can solve that for dy dx. I'm going to keep everything on the left that has a dy dx. The 2y plus 3 dy dx equals to the negative of the 2x minus 2 dx turns into 1, so I'm going to leave it like that. Divide both sides by the 2y plus 3, 2y plus 3. Here's my final answer. Dy dx equals to the 2's cancel, the negative of the x minus 3 over y plus 3. There's your derivative of that implicit function. Why did he want me to do that derivative? Complete the table below, finding the value for each of the indicated points. Oh, we're going to actually find the slope of that circle at various locations. 0, 2. So 0, 2 is right here. That's what it looks like graphically. We've done this problem before, estimating different derivatives of a curve just by estimating, but I don't have to estimate anymore. Because if I know that my slope is y prime, which is dy dx, is equal to the negative of a y minus 3 over, or I mean x minus 3, over y plus, oh, my numbers are wrong. That's a 2. That's a 2. That's a 3. Okay. I'm sure some of you were thinking that the whole time. Well, actually, it was a 3. The y is a 2 part. Yeah. Was an x I think I have everything up in there. It was an x minus a 3, doggone it, and a y plus a 2 the whole time. X minus a 3, y plus a 2, x minus a 3, y plus a 2, x minus a 3, y plus a 2. How come you didn't tell me? Nobody said a word to me. That's how polite you all are. Okay. So now that I wrote it correctly, x minus a 3, y plus a 2, I am going to do my dy dx at 0, 2, which just means I plug in the x as 0 and the y will be a 2. So in the top, if x is 0, it really doesn't matter. Let's see. If y is a 2, so that's going to give me a negative. 0 minus 3 just gives me a minus. Minus 3 is 3 over the 2 plus 2 is 4. So in my imagination, I would love to think that I have a positive slope of 3/4. Let's just see if it's close. 1, 2, 3, 1, 2, 3, 4. Hey, better than government work. It's a good thing I caught my mistake, though. Second one. All the hard work is done now. I just need at 3, 3. And graphically, 3, 3 looks like. I'll do it in blue. 3 right, 1, 2, 3. Oh. What are you predicting? What are you predicting? You better be saying 0. I'm a bad artist, but I can handle that. My slope at 3, 3 would be a negative of a 3 minus 3 divided by 3 plus 2. And the 3 minus 3 is 0, negative 0 is 0. It doesn't matter what I divide by. 8, negative 2. 8, negative 2 is here. Tangent line. That's what the derivative is. The slope of the tangent line. What are you getting? You better be saying undefined. That's where the derivative does not exist. So I'm looking for y prime at 8, negative 2. That's where I was, right? 8, negative 2, I certainly was. Would be equal to negative of the 8 minus 2 over a negative 2 plus 2. Just plugging it into the same derivative is negative 6 over 0 undefined. I love how a plan works. One more, then I'm moving on. 3, negative 7. So I'll be looking for y prime at 3, negative 7. Let me find 3, negative 7. 1, the 3, negative 7. Oh, 3, 1, 2, 3, 4. So, well, that's not exciting. I have a feeling that should be 0. Let's do it. plug it into the same derivative formula. Negative of a 3 minus 3 over, why am I working so hard? Negative 7 plus 2 is a negative 0. It's a 0 again, regardless. Regardless of the denominator. Oh, do I want to do one more? Not really. 6, 2. 6, 2. Looks like some sort of a negative slope. Let's try it. 6, 2. Y prime at 6, 2 will be negative of a 6 minus 3 is minus 2. It is minus 3. What am I doing? 6 minus 3 over 2 plus 2. That's easy. That's a 4. Gives me a negative 3. No. 6 minus 3 is 3. Yeah, negative 3 over 4. Well, at least it's negative. Let's see if it could be a 3/4. Start right here. Negative direction, obviously. 1, 2, 3. 1, 2, 3, 4. Yeah, it works out pretty good. I hope you got the idea. Finish those two. I will be expecting to see those done in your lecture notes. If you don't do them, then I know you didn't watch the video. Or you just copied somebody else's notes and they didn't do it. All right, let's find the derivative of each of these implicit functions. So I'm going to do this with all the steps. I'm going to even rewrite it so I have more room. What I mean by more room? Because I have to take the derivative with respect to x, both sides. When I do the derivative of a y, I always have to say it's 2y dy dx. On the right side, the derivative of 2x is technically, that was a y right here anyway, 2, obviously the derivative of x is 1, dx dx, plus 3, derivative of y is 1, but I have to also say I'm doing it with respect to dy dx. So every time you do the derivative with an x in it, that just goes away. Every time you do the derivative with the with a y in it, you have to have a dy dx. That is why this just turns into equals to a 2 plus a 3 dy dx. Now I'm not done because I have to solve for dy dx. Move everything to one side that has a dy dx. 2y dy dx. Move the 3 dy dx to the left equals to 2. And technically what we're doing for the left side is we're factoring out a dy dx. That leaves a times 2y minus a 3 equals to 2. So dy dx is what happens when I divide both sides by 2y minus 3. dy dx is 2 divided by 2y minus 3. Now, there are steps in there that the experienced user will probably skip. But just for kicks, I'm not going to right now. I'm going to do the derivative with respect to x to both sides, derivative with respect to x, both sides. That's 2 times 1 dx. And that was an e to the, I think that's to the y. I need to erase that so I can see it. E to the y, so plus the derivative of e to the y. The derivative of e to the u is always e to the u times the derivative of u dy dx equals to the derivative of x squared with respect to x is 2x dx dx minus the derivative of y squared is minus 2y dy dx. Get everything on one side that has a dy dx, and everything else goes the other side. So the e to the y, dy dx stays on the left. The minus 2y dy dx becomes plus 2y dy dx over here. The 2, that just becomes a 2, moves to the right. I'm right, I was right. It moves to the right, it's negative. And I already had a plus 2x dx dx, which is plus 2x. Factor out the dy dx, leaving e to the y plus 2y equals to negative 2 plus 2x. Divide both sides by e to the y plus 2y. It looks like this. Divide by e to the y plus 2y. E to the y plus 2y. Cancels. Dy dx is negative 2 plus 2x over e to the y plus 2y. If this isn't fun, I don't know what is. All right. What happens when we're doing implicit differentiation? Guess what? You may have to use all your rules, your product rules. We just did e to the u. Now we got a product rule. So I'm going to do the derivative with respect to x on the left, the derivative with respect to x on the right. So now I have to do the derivative of 2xy, which is the product rule. So it's the first, that's 2x, the first times the derivative of the second. The derivative of y is 1 dy dx plus the second, which is the y, times the derivative of the first, which is 2 dx dx. The derivative of the first times the derivative of the first times the second times the first equals to, the right side is not product rule. So it's just going to be a 6y dy dx plus derivative of 2x is just a 2 dx dx. And it won't be long where you won't be writing dx dx. You'll just understand that to be true. So when I rewrite it, it becomes 2x dy dx plus 2y dx dx goes away equals to 6y dy dx plus a 2. Put everything on one side that has a dy dx, move everything over. So basically in English, this is moving this way and this is moving this way. 2x dy dx, that cannot go away, minus 6 dy dx equals to a a 2 minus 2y. Factor out the dy dx, leaving a 2x minus 6, 2 minus 2y, and realize that my derivative dy dx is 2 minus 2y over 2x minus 6. That could probably clean up by everything dividing by a 2. 1 minus a y over an x minus a 3 would probably be the best answer. That was good. Product rule. Getting uglier. Another product rule. Left to right. The derivative of the left is 15 x squared dx dx plus 0 equals to 2 dy dx. Since there's a minus in front of the product, I'll do what I did before. Even in the old days, before we had two variables being differentiated. When there's a minus in front of that product, it's safer to pull it out. So now the first is 3x squared, and the second is a y. So the first is 3x squared times the derivative of the second, dy dx, plus the second, which was y, times the derivative of 3x squared, that's a 6x, dx, dx. Try to clean this bad boy up. 15x squared, dx, dx cancels, equals to a 2, dy, dx does not. Distribute your minus 2x, a 3x squared, dy, dx, minus 6xy, dx, dx goes away. Everything with a dy, dx move to the left, or you can go the other way around if you wanted to. Since I already have a dy, dx here and a dy, dx here, I could take the 15x squared and add the 6xy, and then equals to the 2 dy dx minus 3x squared dy dx. Factor out the dy dx on this side, leaving a 2 minus 3x squared, still equal to the 15x squared plus 6xy. I don't know what that was. That's nothing. 15x squared plus 6. Yeah, I don't know why there's a mark there. And divide both sides by 2 minus 3x squared. So dy dx is 15x squared plus 6xy divided by 2 minus 3x squared. Woof, I'm getting tired. Wow, I just did 4 very, very, very tough problems. No guarantee that they're all right, but I'm sure one of you fine people will let me know. All right. In terms of y, describe the values of x for which the curve of x squared plus, was x squared? That's x cubed. X cubed plus y cubed equals to a 4xy plus 1. We'll have vertical tangents. Okay, show your work and explain your thinking. Well, that means I need to do the derivative. So let me start out with x cubed plus y cubed equals to 4xy plus 1, and do the derivative with respect to x, both sides. And that gives me, I don't think they gave me enough room to do all the work. With 3x squared dx, I'll leave off now, plus 3y squared dy dx, I cannot leave off, equals to the product rule. So I'm going to call 4x as the first term. The first 4x times the derivative of a y, which is dy dx, plus a y times the derivative of 4x, which is 4, divided by 4y, plus 0. Move the 3x squared to the right, and move the 4x dy dx to the left. So that gives me 3y squared dy dx minus 4x dy dx has to equal to, that's a negative 3x squared. And I already had a 4y over there, plus 4y. Factor out the dy dx. 3y squared minus 4x equals to the negative 3x squared plus 4y. 3y squared minus 4x equals to, why am I doing that? Oh, I already pulled dy dx equals to negative 3x squared plus 4y, all divided by 3y squared minus 4x. The whole question that they were asking was, in terms of y, describe the values for x, which would make this have a vertical tangent. Vertical tangent would mean your denominator is equal to 0. So I will take 3y squared minus 4x, set that equal to 0, and in terms of y means solve it for y. What value, well, actually, what value? Describe the values for x. What values of x? Okay, so I'm solving for y. I thought I was solving for y, but I think I'm solving for x. What values of x? Negative 4x would equal to negative 3y squared. 4x is 3y squared. X would equal to 3y squared divided by 4. When x is equal to 3y squared divided by 4, that doesn't seem to be very pretty. I don't even know if I can make it even better here. Vertical tangent occurs when the denominator is 0. So I'm going to leave it like that. I'll get back to you if you wanted me to. It'd be silly to solve for y, because what would happen if I solve for y, I'll just do it for fun. Y would be the square root of 4/3 x. You can go both ways, so just depending on, I'll get back to you if I see anything else on that one. You mean I can find a second derivative? Yes, you can. But let's first do the first derivative. Derivative of both sides gives me 2y, y prime, plus 2y prime equals to 2 plus 0. Factor out my y prime. 2y plus 2 equals to 2y prime is 2 over 2y plus 2. We want the second derivative. So when I do the derivative again to both sides, when I do the derivative with respect to x, both sides, I end up getting my second derivative, dy with a 2 inside, dx with a 2 on the outside. That's your second derivative. That's when you take the derivative of y prime. Will equal to, you could use quotient rule for this thing here, y plus 2y plus 2 times the derivative of the top, which is 0, minus 2 times the derivative of the bottom, which is 2 dy dx. That's it. Your second derivative is equal to, your y double prime is equal to a 0 minus 2 times 2, which is 4 y prime. But you can't leave a y prime and a y double prime in the same problem. So you have to take your answer I had right here when I said y prime is equal to 2 over 2y plus 2. I have to substitute that into here. So my second derivative is equal to a negative 4 times that first derivative, 2 over 2y plus 2, which is negative 8 over 2y plus 2, which can reduce a 2, negative 4 over y plus 1. There's your second derivative. One more. And I'm getting lazy with my notation because I'm tired, but in real life, we don't really do all that detail. We just say derivative of x squared is 2x, dx dx, we know in our head goes away, plus derivative of y squared is 2y, y prime. Derivative of 1 is 0. Solve it for y prime is the negative 2x over 2y, which is negative x over y. Now I have to do my second derivative. Second derivative, derivative of y prime is y prime. Will be the quotient rule. Y times the negative 1 minus the top, negative x times the derivative of y, which is y prime, all over y squared. So it looks like y double prime is a negative y plus an x y prime all over y. But you can't leave a y double prime and a y prime in the same problem. So you're going to have to take your y prime, substitute it into here. So your best answer, y double prime, is negative y plus an x times negative x over y, all of that over y, negative y minus x squared over y, all over y. I can do better, equals the negative y over y minus x squared over y squared, which is negative 1 minus x squared over y squared. I can still do better, is negative y squared minus x squared all over y squared. I'll let you chew on that simplification. And the only homework you're going to have, oh, good, is those 4, all of those. And the next page, you got 3 more, all of those. So we'll stop here. Adios, hasta luego, and save this for another day.